Hello and welcome to T Academy. In today's lecture, we'll be starting our discussion on boost switching regulators. In the previous few lectures, we were looking at buck switching regulators. We looked at the basic waveforms, switching losses, conduction losses, voltage regulation, as well as worked out a design example. Now we are starting a lecture series on boost switching regulators where we will cover the same topics. Now, as you saw with the buck switching regulator, the major limitation was that the output voltage V0 is less than the input voltage VDC. Now with a slightly different topology, as you can see in this diagram, we can get a regulated output voltage that is greater than the unregulated input voltage. Here we have an inductor L0 in series with the supply voltage and a switching element Q1 connected to ground. The inductor stores energy in its magnetic field during the turn on period, and during turn off it supplies this energy to the output load as well as this capacitor through this diode D1. Now let's look at the turn on and turn off operations. Now during turn on, Q1 is connected to ground, therefore this point is at zero potential. The diode D1 therefore becomes reverse biased and no current flows to the output load from the input. The inductor L0 gets charged and its current rises to a peak value given by VDC divided by L0 times T on. And if this is a period T and assuming 50% duty cycle, we have a turn on period. The inductor current IL can be plotted as linearly increasing from 0 to a value equal to I peak during this duration of T on. Now during T off, there is no connection to the ground, and the current that was established through the inductor during T on must continue to flow in the same direction as the inductor doesn't allow an instantaneous change in the current. Therefore, the polarity of voltage across the inductor terminals has to reverse, where the undotted terminal becomes positive with respect to the dotted terminal. And the energy that was stored in the magnetic field of the inductor is now supplied to the output load via the diode D1, where it not only provides current to the load, it also replenishes the charge that was lost by C0 during T on operation. Therefore, the current I peak, which was established during T on period, now it decays linearly back to zero during this T off period. So this period is the T off period. So from here you can see that the output voltage V0 is equal to VDC plus the voltage that was developed across the inductor. Therefore, V0 is boosted to a value that is greater than the input voltage VDC. In the next lecture, we'll see how the output voltage V0 is regulated based on a feedback loop like this. We looked at the PWM control for a buck switching regulator. Now in the next lecture, we'll see how the output voltage V0 is maintained in a boost converter with PWM operation. So thanks a lot for watching and see you in the next lecture.